Hello, and thank you for the invitation to present at the Symposium. I'd like to present this work regarding Striatal Bayesian beliefs and self-efficacy in a sample of adolescents. I have no disclosures. So this is an example of applying computational modelling to some brain imaging data in a clinical context, whilst attempting to avoid some of the pitfalls which my colleagues have spoken about. It's a pilot study whose purpose is to determine whether a reward-based fMRI paradigm that probes the value that we place on being able to make our own choices, if that's able to provide a meaningful account for brain activation in a group of adolescents, and whether this has any face validity in terms of measuring self-efficacy, autonomy, these properties, and also if that relates to depression. So depression is the focus clinically here, and it's often an illness which has its roots in adolescence. According to best estimates, about 25% of people who have depression already had it by the time they were 19. So, however, it's also a very, if not the most heterogeneous illness within psychiatry. And this umbrella term probably captures a lot of different manifestations, each one with their own particular neurobiological origins and therefore arguably amenable to different therapeutic interventions. So, I mean, there are many different ways to stratify the people under this particular umbrella. This pilot study, the hope is that if we can zero in on a feature that has high potential to have a profound impact on somebody's developing life course, that could yield the greatest benefit in terms of intervention. So the proposal is that that quality of autonomy or self-efficacy, that belief that you have to, in your own ability to plan and execute goal-directed behaviour, is something which, during adolescence, it's supposed to be a property which is proliferating, you're discovering more, you're pushing the boundaries and finding out what you're capable of, what you can do. As a quality, it's known to promote resilience and recovery from adversity or illness. And it is one of those things which is both impaired and, in a vicious circle, impairing in depression, in that there's that sense of opportunities being lost, doors being closed, and this is a process which would be very good to interrupt. So another well-replicated finding within the depression literature is that the reward network appears to be dysfunctional, with blunted anticipatory responses to reward seen within the striatum specifically, and other regions as well. This is potentially the means by which self-efficacy is disrupted in itself in depression. Some recent work by Rouen and colleagues suggests dysfunction in similar overlapping areas. So the intention here is to look at reward network dysfunction through the lens of self-efficacy, given the potential impact that it has on the development and recovery of a young person from depression. So to do this, we have this modified associative reward learning task. It's designed to allow you to key in on that moment when you were told that you get to do the choosing, and compares that to the time when you are told that the computer is going to be telling you what to do and you just have to do what it says. So over time, you're learning which one of these cards is the most rewarding to select. You choose one, you get the reward. The other half of the time the computer tells you what to do and you get crucially the same rewards. They are matched across the trial, the whole experiment, but now we can model this particular phase of the task. So we've previously demonstrated in a large adult sample of subclinically depressed people. So you can see the spread of scores here on the QID scale. There are a number who have significant depressive symptoms without being formally diagnosed, but the majority are healthy controls. We found that that anticipatory signal of being able to choose in itself in the ventral striatum correlated with those depressive scores. So in this particular pilot study, as a proof of principle, we were hoping to use this task in obviously a very modest sample of adolescents and early adults, who were recruited on the basis of having experienced depression either currently or in the past. And we used the PHQ-9 to kind of screen for that. The mean score for them was 11. 10 would be the screening cutoff for possible depressive disorder. 15 would indicate a moderately severe illness, and 20 would indicate a significant depressive illness of severe intensity. So overall, our opportunistic sample here just have a good spread over the possibilities. So they were imaged at 3 Tesla, TR 1.4, for a total of about 12 minutes. And the computational framework that we've applied to this data is the Hierarchical Gaussian Filter, developed by Mattis and colleagues. This infers one's beliefs about the causes of your sensory inputs down at this hierarchical level, based on what we observe them to be doing, their behavioural data. And over a series of increasingly abstract hierarchical levels, the beliefs of those causes are modelled, and then the mismatches between those beliefs and the apparent input from the level below is used to update beliefs accordingly, and these crucially are weighted by the precision of that belief, how certain that belief is held. Within a Bayesian context, obviously if you're extremely sure, you have a high level of certainty or precision about a particular belief, it takes a lot of very precise evidence to move that posterior accordingly. If it's much more ambiguous, then it doesn't take as much evidence to adjust your belief on the next cycle. So in this particular case, in our model, as a skeleton model, it's operating over 3 layers. The lowest level is simply whether or not the yellow card in this instance leads to a reward, that particular sensory contingency. The next hierarchical level up is modelling the tendency for the yellow card to be rewarding over time. And the level above that is to ask how variable that in itself is over time as well, so that volatility. We've separated 2 basic conditions, so this represents when you, the participant, gets to do the choosing, and this represents the trials when it's the computer who's doing the choosing. The crucial element here is that this is, we take to characterise self-efficacy. This is the tendency for yourself, in this instance, to be correct most of the time, versus the computer to be correct most of the time. It's representing that belief in your ability to do this task well, fundamentally. This generative model operates as a series of Gaussian curves with a random walk in between each level, and a sigmoid at the slowest level for the decision itself. So, rather than just testing a single model, we compared it to some possible simpler possibilities to see if the elaborations were worthwhile and if they actually represented something meaningful. So at the very basic level, we just had a simple Rescola-Wagner model of attempting to capture the value of the choice versus the no choice conditions over time, and using the prediction error to update that. There's no belief per se, it's essentially a model-free model, if that makes sense, and that has a simple softmax function to generate the response. The first hierarchical Gaussian filter is one that has 2 layers, so one with the basic sensory input and that simple belief above it. Again, with one side having a softmax function as a response. And the other implementation, crucially, the sigmoid steepness, the curve, is modulated by how certain you are in your own tendency to be correct. So that's what this represents here by the x2 uncertainty. And then we have a 3-level instantiation of both of those, where the volatility of those beliefs is in itself modelled. There's a number of free parameters associated with each one, and we use Bayesian model selection based on the behavioural data to determine which is the best one. The Bayesian model selection had the strongest support for the model, which had 3 layers, including that top volatility layer, and crucially used the level 2 uncertainty to modulate how precise and crisp the decision-making process was. Some support for that same process at 2 layers, but 3 layers is the clear winner. Establishing whether or not this model performed better than chance for each individual participant. The negative log likelihood per trial was greater than 0.55, which is a way of saying that it's better than chance for everybody who was included in our study. One person it was close, but for everybody else it did a good job. So, taking the behavioural data to infer the beliefs, these beliefs and crucially the uncertainty surrounding that belief was taken from the second level and used to modulate the onset of each trial when they were told that they were going to be making a decision or that the computer was going to be telling them what to do. And these contrasts were taken to the second level for random effects analysis. Considering just the basic belief itself, at the whole brain level, this didn't report anything of significance. However, when we looked at the uncertainty surrounding that belief, this did seem to provide a good account for activation within the reward network and some executive functioning regions as well, notably the caudate, the ventral striatum, and this was quite a robust response, no small volume correction, cluster-wise significant at the whole brain level after multiple comparisons correction. To establish whether or not this was specific to the 3-level HGF, we also looked at whether or not the simple Riscola-Wagner model did a good job. This was, as you would hope, given it's Riscola-Wagner, picking out some striatum as well, but nowhere near with the level of robustness and good account that was provided by the 3-level HGF. So that supports its utility. So the next step was to establish if this activation that we've identified had any face validity with the measures of interest. So we keyed in on these 10 regions that emerged as statistically significant and wanted to see how they performed in terms of relating to 7 psychometric measures of interest. PHQ-9, a measure of depression, very well validated. The general causality orientation scale, this comes from self-determination theory and is broken down into 3 elements. First, the sense of autonomy. This is the degree to which somebody is intrinsically motivated. They're interested in doing things for their own sake, because they're interesting, to garner information, for challenge, that kind of thing. The control orientation, these people are a bit more externally motivated. They respond to rewards, to deadlines, to these kinds of things. And an impersonal orientation. These people tend to believe that most aspects of life are beyond their control, and there's more of a tendency to believe in destiny and fate. The perceived choice and awareness of self scale, also from self-determination theory, looks at the degree to which you feel like you have control of your own behaviour and you have choices. And the awareness of self is that sense of awareness of your own inner states and what you're all about, that sense of self in itself. And then finally, the brief resilience scale, that ability to bounce back from a setback. So doing this analysis in a rigorous way, obviously there's likely to be a lot of multicollinearity, so we used the Mixomics toolbox to apply sparse partial least squares regression to the 2 different modalities, brain extracted activation and our 7 psychometric measures of interest. This was performed in a nested cross-validation framework, optimising first to find the optimal numbers of features to be included, which provided the best prediction of the full model, and then a second nest to determine which particular features were the most reliably, stably selected for any given iteration. And then once that had narrowed down which were most optimal, then we use some confirmatory stepwise regressions to establish significance of those features. So, taking a look at self-uncertainty and psychometrics, this found that 2 brain features was able to provide an account for 3 psychometric features. It was the same 2 regions that kept emerging as being the most often selected, and the same 3 for the psychometrics. Specifically, it turned out to be left caudate's representation of self-uncertainty, and the same correlate in the more ventral striatum on the same side. It was the case that the higher the level of self-uncertainty in this area, the higher your symptoms of depression, and the more likely you were to have this impersonal causality orientation, tending towards feeling out of control in your own life, and the lower your sense that you were able to make choices and able to control your own behaviour. Within some confirmatory regressions for these three measures, it was indeed the case that the left caudate emerged as the most dominant factor, most robustly for perceived choice, but also significantly for depression, slightly less so for the impersonal orientation. And in terms of seeing how these scatter, obviously we're bearing in mind that this is quite a small sample. It doesn't appear to be driven by outliers. It does seem to capture the variance within this particular group fairly well. So taking this particularly prominent brain feature, the left caudate's self-uncertainty representation, and then doing a stepwise regression according to the individual items of the PHQ-9. This again provided a good account for the data in itself, with the two standout symptoms being anhedonia, the loss of enjoyment of things that would normally be enjoyable, and self-regard, self-esteem, feeling not so good about yourself. So in terms of specificity, when we looked at the other condition where the computer was doing the choosing and the belief uncertainty associated with that, the cross-validation process did narrow down to right caudate and the SMA. However, the confirmatory regressions didn't report any of these as being actually significant. And focusing on the left caudate, again, relating that to the individual PHQ-9 items, again, there was nothing like the high level of account that we saw during the self-uncertainty condition. So it did seem to be more specific to that rather than belief in general or uncertainty in general. So to summarise, this is a pilot study. It's here to demonstrate proof of concept of this task within this group of people. It's not here to generalise. Obviously, we need replication to do anything in a meaningful sense on that side. The optimal model involved using that person's uncertainty to modulate their decision-making ability. That beat all the other models. And it was able to provide a better account for reward network activation than simpler computational models. The multivariate approach, attempting to encompass all of that collinearity in a meaningful way, did provide some face validity for the task in itself, particularly with regards to self-belief representations in the left caudate. That was correlating with the sense of being able to make your own choices and being able to experience pleasure and positive self-regard. So the proof of the pudding will be in the eating. This has the potential to be useful if it can demonstrate change in response to therapeutic benefit, or particularly if it was able to anticipate therapeutic response to certain interventions. I'd like to thank very much our young participants who were really enthusiastic in taking part in the study, and all of my wonderful colleagues. Thank you.